Today concept is about optimization of basic blocks. What it means is in the last class I explained about how to construct the DAG from the basic blocks, from the given basic blocks. What it means is the input is in the form of an basic block and we construct the DAG for the input and we show the output in the form of an DAG representation. And here what the step number 2 is to optimize, to perform the optimization of the basic blocks. Here in this I am performing two transformation techniques, and what the transformation techniques are. The first one is a common sub-expression elimination where it is from the principal optimization. It is a transformation from the principal optimization, and here by the construction of the DAG I am applying this transformation. What the name of the transformation is? It is a common sub-expression elimination. And I already explained what the transformation, I explained about the common sub-expression elimination. And what it means is, again, I'm repeating that, it is an expression appearing repeatedly in the program, which is computed previously. Make a note of this. Appearing repeatedly in the program and which is computed previously. And that we can call them as an common sub-expressions in the given expression. So one thing we need to remember that here for eliminating the common sub-expressions, we are actually targeting for the expressions that compute the same value. Which computes the same value, we are eliminating those common sub-expressions, right? If it is already appeared in further, and again we are doing the same computation, again we are continuing the same computation, then if we find out such computations we can eliminate, but just by naming it as a common sub-expression, where we are applying the transformation like in common sub-expression elimination from the principal sources of optimization, we are eliminating that. And see here we're having an example: a is equal to b plus c, b is equal to b minus d, c is equal to c plus d, e is equal to b plus. These are the three address statements, right? And here, where and where we're having the common sub expressions, we're having the common expressions at a is equal to b plus c and at e is equal to b plus c, because both the a and e are computing b and c, with the same operator place. So we need to eliminate that. We're finding out, we find out that it is a common expression in the given three address statements. So we need to eliminate that. And this is before transformation. After transformation, what the code is: a is equal to b plus c, b is equal to b minus d, c is equal to c plus d. We eliminate one expression here. And here, why we are not eliminating here, why we are not showing the transformation, it means, but here the results do not generate the same value. That means if we compute for the same value, that means the computation for the same values, whenever the computations for the same values are done, then only we need to eliminate them just by applying the transformation. But those are common expressions but do not generate the same results. And here this is the first technique that we're applying in optimization of basic blocks. The name of the technique is in common sub-expression elimination. It is from the principal sources of optimization. Here we're applying this technique by the construction of DAGs. And just by taking the basic block like an a is equal to b plus c, b is equal to b minus d, c is equal to c plus d, e is equal to b plus c, we find out where the common expressions are. Then after finding out the common expressions, just actually after applying the transformation, we need to show what the code it is, right? Then but here we are not showing that. Why? Because here these whatever the variables we are having like an a and e, those variables are not generating the same result, right? So, and what the next technique is, and what the next technique that we're going to apply in this optimization of basic blocks is that is an, this is the DAG representation for this, for the common sub expression elimination. A DAG representation, what it identifies is identifies the expressions and that yields the same result. Before and after both are same, right? But here just we're modifying, or we're replacing the B with an B naught and C with an C naught and D with an D naught. Why? Because the right hand side computations are between A, B, C, D. There is no A variable. So the resultant variables are also A, B, C, E, like that. So instead of defining the statement with the variables, just we are using the computations with B naught, C naught, D naught, and so on, like that, right? And this is the DAG representation of the common sub expression. And here the second technique, that is and dead code elimination. I think you all know what the dead code elimination is, because this is also the transformation from the principal sources of optimization. And there itself I explained what the dead code elimination is. A variable is said to be live in a program if the value contained into it is used subsequently, then only it becomes a live variable. Otherwise, it is a dead variable. Make it clear. When we said that it is a live means, live in a program means the value contained into it, if the value contained into it is used subsequently. For example, A is having some value, B is having some value, D is having some value, and C is having some value. When you use the value subsequently, then only we can say that that variable is an live variable. Otherwise, it becomes a dead variable, right? I think you all understand, because this I explained this in principal sources of optimization. This is the most important transformation for having at principal optimization. And see how to eliminate the dead code elimination. The code generation from the DAG eliminates the dead code. Initially, I represent an DAG from the given basic block. Here my basic block consisting of the 3 address statements. And from the DAG, after transformation, what my code is, what my basic block looks like. My basic block consisting of A is equal to B plus C, D is equal to A minus D, C is equal to D plus C. See, the both B and D variables are computing the same variables, A and D, with the same operator. So I'm choosing one, where why I choose the one means B in here, the B variable, if the value contained for the B is not at all used in further, it is not at all used subsequently. So I'm eliminating the B, and instead of B I am using the D. That's the process of applying the transformation for the basic blocks. And from the DAG also we can easily find it out where the dead code variables are. And after the optimization of basic blocks, and here the next concept is about the loop optimization. And what I explained in the last class means, in the last class it is about the optimization of the basic blocks, right? And initially I start with what the basic block is, or what is a basic block, and then what the terminologies used in basic block, and then the transformations of the basic block, the transformations of the optimization of the basic blocks. And by learning with the first transformation, in the first transformation we are having the two-step procedure, right? Two-step procedure. What the two-step procedure is, actually the first transformation is a structure preserving transformation, right? While performing or while applying this structure preserving transformation, what the first thing we need to do is, first we need to construct the DAG, and then we need to apply the transformations. Is it clear? What it means is, the structure preserving transformation is a DAG based representation. So first initially we need to construct the DAG, and then construct the DAG for the basic blocks. Then the above said informations can be applied. What the above said transformations means, those can be principal sources of optimization transformations. So in here, this dead code elimination is a principal source optimization transformation, and as well as the common sub expression is also an transformation from principal sources of optimization. Is it clear now? With this, the structure preserving transformation is completed. The structure preserving transformation is completed in optimization of basic blocks. Now I'm going to learn about the second, we're having the second transformation, like use of algebraic identities. I already explained about this algebraic identities at at peephole optimization. And there algebraic identities or the algebraic simplification is same. Instead of using 2 into a, we can use a plus a, or instead of using a by 2, we can use 0.2, like that. What it means is use of lower strength operators instead of higher strength operators makes the code efficient. In such a way, we are using those algebraic identities like a plus 0 is equal to a into 1 is equal to a, or a by 1 is equal to a. All these are all the algebraic identities. And these algebraic identities are used in peephole optimization techniques. And also some simple transformations can be applied in order to optimize the code. In what the simple transformations are, like a plus 0 is equal to a into 1 is equal to a or a by 1 is equal to a. That means the corresponding identities can be applied on corresponding algebraic expressions. And here the algebraic transformations can be obtained using the strength reduction technique. Make a note of this. Using the strength reduction technique, we are obtaining this algebraic simplification or algebraic identification, or we can also call it as an algebraic transformation. And just by giving an example, like instead of using 2 into a, we can use a plus a, or instead of using a by 2, we can use a into 0.5. And here what we done an strength reduction technique. That means we obtain the strength reduction technique. And what the strength reduction technique is, here we use a lower strength operators instead of higher strength operators to make the code efficient. Making the code efficient, we are using such type of an transformations. And also we are having the constant folding technique that can be applied to achieve the algebraic transformations. With the constant folding technique and with the strength reduction technique, what we are doing is we are applying these to these transformations in peephole optimization or at the optimization of the basic blocks, just to achieve what to achieve here, only for achieving the code efficient, right? So these are the two techniques that we are using at algebraic identities or algebraic transformations. And here what the next concept is, loop optimization. This loop optimization I already explained to you all. I already explained about the loop optimization. And what is a loop optimization? Here, the optimization can be significantly done in loops of the program. Make it clear. Here, the optimization can be significantly done in loops of the program. Especially we are choosing the inner loops, because inner loops is a place where the program spends a large amount of time. And here the number of instructions are less in inner loops, then the running time of the program will get decreased to a large extent. And by using this technique like a loop optimization, here in which code optimization is performed on inner loops. Whatever the transformations that are carried out, or whatever the methods that we are carried out, we are applied only on the inner loops by using these loop optimizations. And here or what the transformations that are under the loop optimization is: loop invariant code removal, or induction variable strength reduction, induction variable reduction. All these comes under the transformations of loop optimization. And here the concept is about a loops in flow graph. First, initially you need to know what is a flow graph. Then you can go for what is a loop, and then what the dominators are, and then how to represent the flow graph and the dominators. And first, initially you need to know what is a flow graph. A flow graph is a directed graph. Make a note of this. A flow graph is a directed graph. And here the flow control information is added to the basic blocks. The flow control information is added to the basic block. And what the constraints we need to remember here is the nodes to the flow graph are represented by the basic blocks. And the blocks whose leader is the first statement, that we can name it as an initial block. And here there is a directed edges. We are having an edges, right? So there are directed edges from block 1 to block n, but the block B1 to edges from block B1 to block B2. That means if B2 is immediately follows the B1 in the given sequence, we can say that B1 is an predecessor, successor and predecessor we are having, right? B1 is a predecessor of B2. We can call it as a B1 is a predecessor of B2. And here our examples to show an example for the flow graph means, to show the example for the flow graph, we need to represent the graph, right? So what the input is here, the input is always in the form of a three address code, like I is equal to 1, T1 is equal to, T2 is equal to, all everything, the code should be in an three address code. By considering the three address code, we are constructing the flow graphs, right? And here we understand what the flow graph is by the definition, and then what the rules or the constraint that are having for the flow graph. That means which can be represented as in basic blocks and which is called as an initial block, and when to say it is in predecessor. And these are the important terminologies that we know just by knowing the definitions. And now what what is a loop? And after knowing about the flow graph, and now we need to know what is a loop. What is a loop? Loop is a collection of nodes in the flow graph. If you know what is a flow graph, then automatically you can know that what the loop is a collection of nodes in the flow graph. By knowing the definition of the flow graph, now we are getting the definition of the loops. Loop is a collection of nodes in the flow graph. And here also we are having some constraints for the loops. And what are those constraints means? All nodes, where all nodes, for example 1 2 3 4 5 6 some n 1 to n, we're having n number of nodes in my flow graph. All such nodes are strongly connected. They should be strongly connected. What it means is, always there is a path from any node to any other node within a loop. Make it clear. Within a loop. A path from within a loop. And next, the collection of nodes has unique entry. And here there is only one path from a node outside the loop to the node inside the loop. That we can call it as a collection of nodes has unique entry. That means from outside the loop to the inside the loop, it is only having an unique entry. And what the next thing is, the loops that contain no other loops. That means that can be defined as an inner loops. Right. The loop that contains no other loops is called as an inner loops. And this is about the definition of the loop and the constraints of the loops. And up to now, I think you all understand what the flow graph is and what the rules or what the constraints of the flow graph. Or we can say that what the terminologies under the flow graph is. That is an initial block or basic block or predecessor of, or which can be called it as a predecessor, like that. And here also, from the concept of the loops, I think you all understand what the definition of the loop and what the rules to be considered under the loops. And here our concept is loops in flow graphs. Here we are introducing with some common terminologies being used for loops in the flow graphs. And what the common terminology here is dominator. And now I know what the flow graph is, and now I know what the loop is. And now I'm going to learn about what the dominator is. In a flow graph, everything in a flow graph, after knowing the definition of the flow graph, then after that, whatever the concept I'm learning, I'm taking the example in the form of a flow graphs. So always I'm called in a flow graph. At the definition of the loop also, loop is a collection of nodes in the flow graph. In such a way, I defined the loop. And here, while coming to the dominators also, the input is in the form of a flow graph here. So, in a flow graph, a node D, make a note, a node D dominates N, dominates the node N. What it means is, every path to node N from initial node goes through D only. This can be denoted as D, see here, we are represented as D dom N. D dom N. What it means is D dominates N. A node D dominates N. Right. When it dominates N, every path to node N from initial node goes through D only. Then only it dominates N. Right. And here every initial node dominates all the remaining nodes. That means because it is the starting of the node, it should dominate the remaining nodes in the graph, in the flow graph. And similarly, every node dominates itself. Just by how we are making a self loops, like that only, every node dominates itself. Right? These are the conditions, and this is the definition about the dominators. And how to define the dominator, because dominator is one of the terminology in loops in flow graph. And how to define this dominator means D dominates N. What it means is the node D, initially node D dominates and node N. When it dominates, we need to know when it dominates, every path to node N from initial node goes through D only, then only it dominates. It dominates N, and that is represented as D dom N. Is it clear now? And here we are having an example. See, this is the example for the dominator tree. This is an example for the dominator tree. What it means in the, see here from the flow graph we are representing the dominators. From the flow graph only. In the flow graph we are representing the dominators. And the initial representation is for the flow graph representation. And from the flow graph we are representing the dominator tree. And here the node 1 is an initial node, and it dominates every node as it has an initial node, because one is an initial node, it dominates the remaining nodes. And node 2, node here, see, node 2 dominates no node because no node is there under the 2. And coming to the 3, node 3, see, node 3 dominates node 4. Based on the directed path, we can say that which node dominates the which node. And here, one see the node 3, 2 dominates no node, and coming to the node 3, dominates 4, 5, 6, 7, 8, 9. And coming to node 4, it dominates 5, 6, 7, 8, 9. Right, and 5 is not having it does not dominates any node, and 6 dominates no node. And coming to node 7, it dominates 8 and 9, 8, 9. And this is the way of seeing how the D dominates the N, because we know the representation, and we know how, when we can say that it is a dominator. And if every path to node N from initial node goes through D only, then we can say that it is an D dom N, right? So this is the way of representing the dominators, and this is the definition of the dominators. About the these are all about the dominators. And next, what is natural loops? These are some types of loops here we're having. What is a natural loop? Natural loops. Loop in a flow graph can be denoted by N tends to D. N tends to D. What it means is D dominates N. Means, for example, again I'm saying that, for example, we're having that P tends to Q. P tends to Q. And here Q becomes an head. Q is a head and P is a tail. Make a note. Q is a head and P is a tail. P is not an head here. P is a tail. Q is a head. What it means is head dominates tail. Head dominates tail. And that's the definition of the natural loops. And that's the representation. It is always denoted by N tends to D or P tends to Q. And what it means is D dom N. And here we're having the edges, and these edges are called as in back edges. And for a loop, there can be more than one back edge in a natural loops. We can have more than one back edges in natural loops. Is it clear now? And after knowing how to represent the dominators, and now the concept is about different types of loops. And here I explained about a natural loop, and now we're having the other loops like loop interchange. Loop interchange. What the meaning of the loop interchange is? Exchanging inner loops with outer loops. It can be called as an loop interchange. Loop splitting. What is a splitting, or what is a loop splitting means? Here we need to simplify a loop. Why to simplify means we are just attempting that to simplify a loop. or we need to eliminate some dependencies just by breaking it into multiple loops, and which have the same bodies but iterate over different contiguous portions of the index range. Then that we can call them as an loop splittings. And another one is an loop peeling. And here we are simplifying a loop with a problematic first iteration and then performing that iteration separately before entering into the loop. Then we can call that as an loop peeling, right? And loop fusion. Loop fusion means here we're talking about two adjacent loops. These two adjacent loops would iterate the same number of items and their bodies can be combined as long as they make no reference to each other data. Then such type of loops can be called as a loop fusion. And what is loop fission? What is loop fission? Break a loop into multiple loops over the same index range, but each taking only a part of the loop's body, not overall body, only a part of the loop's body. Then we can call that type of loop is a loop fission. And what is loop unrolling? Here, the duplicates the body of the loop multiple times. That means redundancy of the loops, usage of redundancy. Then we can call them as a loop unrolling. These are all the types of loops here. And the next one is a pre-header. Pre-header. And you know what the inner loop is? Inner loop is a loop that contains no other loop. That we can call them as an inner loop. Make it clear. What is an inner loop means? Inner loop is a loop, but that contains no other loops. And here the next one is an pre-header. These are the terminologies under the loop optimization. Make it clear. All these are all the terminologies under the loops in flow graph. And first starting with the dominators and then about the natural loops and then about inner loop and loop fusion, loop fission, loop unrolling and loop interchange, loop splitting and loop peeling. These are all the terminologies of loops in flow graphs. And what is a pre-header? Here a pre-header is a new block. We are creating that block. Why to create means the successors of these blocks is the header block. The successor of the block is an header block. So all the computations that can be made before the header block can be made before the pre-header block. Right? Is it clear now what is in pre-header means? What is in pre-header means what the control flows that use it to enter the loop from outside the loop throughout the header and enters the loop from pre-header. And again I'm repeating that here the targeted to the whole statements that are moved out of the loop. That means once recall what the code movement or code motion transformation is, moving the inside loop to the outside loop, right? So as it is the same, having some same similarities like that. But here what we are doing here is, here we are talking about the blocks, right? So the pre-header is a separate block here. It is created. The pre-header block is created, new block created here. And the successors of this block is the header block. And whatever the computations that can be made before the header can be made before the pre-header block. Is it clear now? This is about an pre-header. And then this is about a loop invariant code removals. And here we're having some loop invariant code removal concept. But before learning about the loop invariant code removal, all of you should know how to reduce the flow graphs. That means reducible flow graphs. What is a reducible flow graph? This is also another terminology in loops in flow graphs. And here there are two types of edges, forward edge and the backward edge. And these edges having some properties like the forward edge form an cyclic graph and the back edge are such edges whose head dominates their tails, and that is about the residual graph. And what is a non-residual flow graph means reverse of that. Again, it is also a flow graph, but there are no back edges, and forward edges may produce cycles in the graph, but in the residual, forward edges form an acyclic graph. But here, forward edges may produce cycles in the graph, right? And these are the two most important terminologies in loops in flow graphs, residual and non-residual flow graphs. Is it clear now? And now what is about an loop invariant code removal? Loop invariant code removal. And here, this is one of the type of computation, one of the type of transformation, we can call it so. Transformation in loop optimization. And what the transformation is, what the name of the transformation is, loop invariant code removal, right? And here we are moving out to pre-header the statements whose source operands do not change within the loop. Whose source operands do not change within the loop. That can be called it as a loop invariant code removal. And what it means is, here in this technique, the computations inside the loop is avoided, and thereby the computations overhead on compiler is avoided. Then ultimately we can optimize the code generation. Ultimately we can optimize the code generation. That we can call it as a loop invariant code removal. And this is one of the most important transformation in loop optimization. And here what the rules we need to consider, it means careful with the memory operations and careful with statements which are executed in some of the iterations. And these are the rules here. And just by taking an example, like a statement is, what the statement is, x is equal to y of z, and it is a loop invariant. And here by using this technique, the computations inside the loop is avoided, and thereby the computation overhead on compiler is avoided, right? So y and z not modified in loop body. S is the only statement to modify x. And for all uses of x, x is the available definition set here. For all exit edge from the loop, S is in the available definition set of edges. If S is a load or store memory operations, then there is no rights to address of X in the loop. And these are the rules. If we are having a statement like that, X is equal to Y of Z, if it is a loop invariant, then we need to follow all these rules. We need to follow all these rules. And this one, again see, the loop invariant code removal can be done without available definition information. What it means is, here we're having the rules that need to change. What the rules is, for all use of X is in the available definition set. For all exit edges, if X is live on the exit edges, is in the available definition set on the exit edges. Approximate of first rule, D dominates in the first rule number 1. Here, the D dominates all uses of X. While coming to the rule number 2, D dominates all exit basic blocks where X is live. And here, and coming to the next type, that is an induction variable, loop induction variable. This is another terminology under the loops in flow graphs. What the induction variable here is, whatever the variables we are using in the code, those variables, that's what it means is, every time they change their value, they are incremented or decremented, whatever it may be, either incremented or decremented. What it means is, instead of increment we are using the add, instead of decrement we are using the sub, right? So here we are having 3 types of induction variables. While considering an induction variable, we are having 3 types. What are those means? One is a basic induction variable, the second is a primary induction variable, and the third one is a derived induction variable. Basic induction variable means, here we are using an assignments within a loop, or for example, I is equal to I plus or minus C, or in the sense by minus C, where C is a constant here. Such type of expressions or such type of statements can be called as an induction variables. Here I is an induction variable. And the primary induction variable is a basic induction variable that controls the loop's execution. For example, if we are using the control statements with for, while, if, like that, then we can use primary induction variables. For I is equal to 0, I less than 100, I plus plus. And here I is and register, it holds an I, a register holding an I. That means it is a primary induction variable. And what the derived induction variable is, it always in a linear function of the basic induction variables. And after knowing what the induction variables is, then we need to know what the types of induction variables are. And see, here we're having an example for this. This is the basic block 1 and basic block 2, where basic block 1 is R1 is equal to 0, R7 is equal to ampersand A, and 2 consisting of all the 3 address codes, That means here, there we're having some loops. So in this, we're having 3 induction variables, right? Basic, primary, and derived. Coming to the basic, the R4, R7, R1 are the basic, the rules. See, in the example, we're having what the R4, what the R7, R1 is. These comes under the basic induction variables. The R1 is equal to 0. It is a primary induction variable. And coming to the R2, where R2 is an R1 into 4, it is a derived induction variable. And here we define from the basic block which one is a basic induction and which one is a primary and which one is a derived induction. And next, here the induction variable strength reduction. Again, here we are creating the basic induction variables from the derived induction variables. Here we need to follow the rules like the statement x is equal to y of z, and what the op is an any type of an operator, star, relational operators, plus or minus, any arithmetical logical units, and y is an variable, right? That means it is an induction variable, and z is an invariant variable here. Z is an invariant variable, and no other statement modifies. It is a loop invariant. With the z, you can show that it is a loop invariant method, and no other statement modifies the x, because x should define the value of the computation that was performed with the y and or z, right? So x is not y or z. X is just a register. It always defines. And here in the induction variable strength reduction, it is a transformation. It is also a transformation. Here a variable x is called as an induction variable of loop L. The value of the variable gets changed every time. That is, it is either decremented or incremented by some constant. And here insert the following into the bottom of pre-headers. We know what the header and what the pre-header is, and now we are inserting it into an bottom of pre-header. And here we are using a function like an inc. The inc function is nothing but an increment of x, whatever it may be, increment of some variable. And with that function, we are calculating the amount of increments for the first parameters. So here how the expression written is, new register is equal to expression of target statement S. New register is equal to expression of target statement S. If opcode of S is not add or sub, insert to the bottom of the pre-header, then what it is, instead of operator add or sub, we need to use inc or dic. Inc is nothing but an increment, dic is nothing but a decrement. So new inc is equal to inc of y comma op comma z. Else new inc is equal to, here I am writing a function for creating an variable x, right? Inc of x. That is, insert the following at each update of y. Then finally it can be written as new register is equal to, because x is a register, right? X is a register. So in the place of x, what I am taking? New register, right? So x is equal to y of z. Is it clear? For the z, I am using new inc, and for the y, I am assigning the same new register. So it can be written as new register is equal to new register plus new inc. And here we can change that x is equal to new register. Is it clear now? With the function inc, we can create the variables here. We can create the variables. And here the induction variables and reduction in strength is only for, we can change the values at every time. Changing the values at every time just by using the decrement or increment by some constants. And this is an example here. This is an example for induction variable strength reduction. See, once get the difference what the initial my flow graph looks like, and after applying the induction variable strength reduction, how my flow graph looks like. R5 is equal to R4 minus 3 and R4 is equal to R4 plus 1. And here what the new register is R4 into R9 and new increment is an R9. So wherever you are having this R9, wherever you are having this R4 into R9, directly you see here we are having, see, there is only change at the initial block and here at the R7 block, because R5 is equal to R4 minus R3 and R4 is equal to R4 plus 1. And after performing the transformation of induction variable strength reduction, my initial block is a new register, it consisting of R4 into R9 and new increment is R9. And here, see here, R4 into R9 is a new register, right? So R7 is equal to new register. And what the new register is? What the new register is equal to R9, right? New increment. So new register is an R4 into R9. So what the new ink is here? R9. So here where we changed is at the initial block and at the block of R7 we done the modifications by applying the transformation induction variable strength reduction. And here to remove the unnecessary basic induction variables from the loop by substituting uses with another basic induction variables, what the rules that we need to follow. First, initially we need to find the two basic induction variables x and y. Then x and y should be in the same family and incremented at the same place, and increments should be equal, and whatever the initial values we are assigning, those are also equal, and x is not live at exit of the loop. For each basic block where x is defined, there is no issue of x between the first and the last definition of y. Make it clear. When we are defining by taking an input from the basic block, for each basic block where x is defined, there is no issue of x between the first and the last definition of y. And these are the rules that we need to follow when we are implementing the transformation like an induction variable elimination. And this is an example, see, and this is an example for the induction variable elimination. Initially my basic block is with R1 is equal to 0 and R2 is equal to 0. Both the R1 and R2 are zeros. And again while coming to the second block, and R1 is equal to R1 minus 1, R2 is equal to R2 minus 1. But here there is no use of using the R1, no use of using this R1, right? So what I'm doing is I'm eliminating the R1, and wherever I'm having the R1, just I'm using it as an R2. I'm making my initial block with an R2 is equal to 0. This is my initial block. This is from the basic block, the initial block is label block is R2 is equal to 0. So just eliminate the R1. R1 is equal to 0. R1 is equal to R1 minus R1. Only we are having, what it means is when I'm calling it as a dominated tree, and this is an initial node, R2 is equal to 0. This dominates the remaining nodes. This R2 is equal to 0 dominates the remaining nodes. That means it dominates R2 is equal to R2 minus 1. And this R2 dominates R9 and R7, R4. And this R4 dominates R7. And R7 also dominates R4 and R7. And this R4 dominates R2. Is it clear now? This is a dominated tree and this is an, both are the dominated trees. But what's the difference here is, here we perform the transformation just by applying the transformation, we get the structure like this. By eliminating an R1 is equal to 0 and R1 is equal to R1 minus R2. See here R7 is equal to R1 into R9, but instead of R1, what I used here? R2. And here R4 is equal to R1, but here it is an R2. Right? Is it clear now? And which node dominates and which node? This is about in basic. In here, I apply the basic induction variable. Here I use in basic induction variable, just removing unnecessary basic induction variables. Here, what my unnecessary basic induction variable is an R1. R1 is an unnecessary variable, so I eliminate that. Is it clear now? And this is a graph like an, here my graph shows about the complexity of the elimination based on what and what. The complexity of the elimination based on the trivial, that means the induction variables that are never used except to increment themselves and do not live at the exit of the loop. and same increment or same initial values are to be discussed. And if it is in same increment, initial values are a known constants. That means offset from the one another. If it is in same increment, nothing known about the relational of the initial values. If it is in different increments, nothing known about the relation of the initial values. And from 1 and 2, those are all basically free, and 3 and 5 required complex pre-header operations. If I want to implement this 3 and 5, I need an complex pre-header operations. But in 1 and 2, those two are basically free. And this is about the complexity of the elimination in induction variable elimination. And here we're having a case like this, same increment but unknown initial value. It is from the case 4. From the case 4, I'm explaining this example at induction variable elimination. And what it is here we're eliminating just by looking at each non-incremental use and generate the same sequence of values as before, right? And here see, R4 is equal to R2 plus 8, right? R3 is equal to R1 plus 4. Here you need to remember that whatever the transformation that we're applying here, that can be done without adding any extra statements in the loop body. Then the transformation can be done. Without adding any extra statements in the loop body, then only the transformation can be done. Otherwise, we should not implement such type of a transformation. Make it clear here. And here I'm having R4 is equal to R2 plus 8, R3 is equal to R1 plus 4. And what R1 is R1 plus 4, R2 is R2 plus 4. And initially I am defining the basic block with Rx is equal to R2 minus R1 plus 8. R2 minus R1 plus 8. And what the R4 is here? What the R4 is here? R2 plus 8, right? Instead of this R2, instead of this 8, this place, this computation, I am using the computation like R1 plus Rx. What it means is, what the Rx is R2 minus R1 plus 8. This R1 and R1 are to be cancelled, and finally it is R2 plus 8. Is it clear now? And the next one is an R3 is equal to R1 is equal to 4. R3 is equal to R1 is equal to 4. But here R3 is equal to R1 plus 4. But what the R1 is, now the R1 becomes 0. So we are assigning the 4 value to the R1. And now here I am eliminating this extra statement because I am eliminating this R2 statement. I am not adding any other statements to the loop body, but I am eliminating this extra statement. R2 is equal to R2 plus 4. And only I am using the statement like an R1 is equal to R1 plus 4. Is it clear? And this is about the induction variable elimination transformation. And the next one is a loop unrolling. Loop unrolling is also the most important transformation here. How to perform the loop unrolling means, here we're having jumps, right? We're having the jumps in the code. And the number of jumps on the test can be reduced just by writing the code 2 times. Just by writing the code 2 times. And what it means is here, replicate the body of a loop n minus 1 times. Instead of writing n times, replicate the body of the loop n minus 1 times. What it resulting in total n copies. And here it enables the overlap of operations from different iterations and also increases the potential of instruction level parallelism. And what the variants are here when we are performing this loop unrolling transformation means, we can enroll multiple of known trip counts. Also we can enroll with remainder loops, also with while loop enrollment. And this is about a loop unrolling. This is also the most important transformation in loop optimization. And with this concept, I am ending the today's session because the loop optimization concept was completed and the terminologies or the transformations under the loop optimizations are discussed. And in the next class, I will discuss the concept of global data flow analysis.